so good morning, everyone. Thanks so much for your coming. So today, we are very excited to have Professor Zhou, from University of Oregon. So you know what? So we have a beautiful weather here today, and in general, so we have a beautiful climate here. And so, but Professor Zhou, he's going to talk about pollution, and that's quite important, particularly given the climate change discussion. Right. So Eric, so you have 1 hour. So we may or may not have questions. So we may just stop you at some point, right?
Yeah.
And so yeah, so we will have some like a Q&A towards the end. Thank you so much for your time. So
All
let me
right.
start
Thanks.
sharing, and then so you can share your slides with us, right?
Okay.
Thank you.
All right. Thanks for having me. I'll try to share my screen. You see it?
Yes, coming. Yeah, great.
All right. Let's try to see if I can do it. Do you see the full screen?
Yeah, so you have quite amazing co-authors.
Great. Thanks.
Uh,
Okay. Thank you. Thanks for having me, especially Zhigang. For those of you who don't know, Zhigang was my macroeconomic professor when I was at Illinois, one of my best professor at Illinois. This is like 6 years since I've seen him. He doesn't appear to age. I don't know, like, what's your secret?
all right.
I'm
So
going to talk about pollution. So
yeah,
title of the talk is From Fog to Smog, the Value of Pollution Information. So again, I'm Eric Zhu, assistant professor at University of Oregon Economic Department. So this work is joined with Pamela Job Barwick and Shanjun Li at Cornell University. So this is basically the work while I was doing postdoc with them. And also with Li Guoling at Shanghai University of Finance and Economics. That's one of the best universities in my hometown. All right, so big picture motivation, I think perfect information is important for efficient decision making, both private and public. But in real world settings, information is often costly to obtain, right? So if you think about like nutritional contents, occupational safety, and taxation, even returns to education, a lot of context information is costly and hard to get, right? So what we focus on this paper is the context of air pollution exposure, not only because I do air pollution research, but I also think there are two things that make it important. One is that in pollution information, pollution is very low salient, right? So a lot of pollutants are often colorless and they don't have smell, so it's hard to feel. And the two is that about limited access, right? So if you look at the 20 countries we know that have the highest level of PM 2.5, only 4 of them that have any format of pollution monitoring infrastructure. Just to give an impression of how kind of bad the problem is in China. So this is a picture, I think, of a northern city in China in 2011, November 27th. What's called a major fog event, right? You can see the picture, it's the middle of the day, you can't see the sun. And this is how the event is reported by the official news media, right? So it says, here's the kind of the Chinese translation, dense fog causes traffic congestion in many northern cities, all right? So a lot of these type of events, especially in the winter, are reported as like fog events. Now the question is this really fog or is this really pollution? So here is a satellite picture of northern China. Now you don't need to know a lot about satellite imageries to know. Just look at this kind of blanket of grayish stuff hanging around the middle or northern part of China. And actually, if you look at satellite measures of pollution, so the measure here I use is called aerosol optical depth. It's kind of measuring how opaque the air is from the satellite point of view. So larger values respond to more particulate pollution, like small particles in the air. And in this figure, you can see the value is really high, right? So near 5. To give you a perspective, in the US, on an average day, the AOD level is something like 0.13, right? So this number is off the scale. It's obviously pollution events rather than a fog event. Right? So I think this reflects a kind of widespread confusion in China at least 10 years ago. So here is a quote from Chai Jing. Chai Jing is a environmentalist turned journalist, and she has this very famous documentary called Under the Dome, millions and millions of viewership in China media. So what she basically said is that we all believed, as a journalist and public, that was fog back then, right? So that's what we call it. I never thought the skies that we see every day could be polluted. I always thought pollution is about mining sites and factory like spewing smoke plumes, right? All right, so what we're going to do today is that we're going to think about this type of, the lack of information and the consequences of people don't have availability of ready sort of access to pollution information. So what we are going to actually do in this paper is that we're going to study China's national air quality monitoring and disclosure program. Right? So the first thing is that there's no public access to pollution data before this program. So pollution was considered before this program a kind of sovereign issue. So you're not supposed to, I mean, you can say that pollution looks bad, you're not going to get arrested or something like that. But if you want to start a campaign that start to tell everybody how bad exactly pollution is, you're very, very likely run into trouble, right? But starting January 2013, I'm going to talk about background, but there's a kind of a watershed moment where the government changed its attitude towards kind of more transparent pollution disclosure. So what they do is that they kind of mimic the US government and installed over 1,400 monitoring sites all across the country, right? So these are US like Environmental Protection Agency grade kind of monitors. They're all automatic. The data, when they're collected from monitors, are transmitted in real time to the government website. And what's important is that not only they kind of sort of collect the data and give it to the government website, they also allow private entities like companies to scrape the data directly from the website, right? So what you see then is a explosion of like mobile apps and stuff came online that broadcast sort of real-time air pollution to residents, right? So this is kind of the treatment we're going to use. And just give an idea what the website looks like. So you don't have to know Chinese to read this. So this is the map of China. A dot here is a city. Red dots are places with high pollution, and green dots are places with low pollution. You can click on any dot here, which will give you, hour by hour record of air pollution in a given city. You can look at any city, any pollution, right? And I don't think this is a real treatment to the extent that my mom is not going to log onto this website and click through. I think the really important thing shown here is the mobile app, right? So after 2013, this program started to roll out. You start to be able to download this type of apps on your mobile phone that tells you, for example, here that in Shanghai, now the air pollution index in Shanghai is about 101. It's called moderately polluted, and it shows you exactly what is the concentration of particulate pollution. All right, so that's basically why my mom is talking about like 8-hour ozone these days, right? So great improvement in awareness. And what's also very useful for the research perspective is that this program is very large. It's not installed like all at once. So there is a staggered rollout of monitoring across 3 waves of cities, right? So some cities get the monitoring network, get disclosure before other cities did. So that gives us sort of quasi-experimental variation to look at the impact of the program, right? So here is how the program basically roll out. I'm going to talk about, the dark color here are cities that get the monitoring first. The sort of, light blue color or the middle light blue color is they got it in the second wave, and the third wave, the rest of the country. And basically the rollout schedule follows a kind of determined city hierarchy, which I'm going to talk about later, giving us sort of quasi exogenous variations in when do the city get the monitoring and data, right?
So Eric,
yeah,
quick question. So if I just eyeballing, so this picture, it seems like they roll out in relatively wealthier part of the country. But this is related to the question. So maybe just go back to the previous slides. I guess you probably have a question. So here, so one question you're interested in, so is that information provision altered awareness, behavior, and health.
Right.
So my feeling is here, so it really requires the citizens, so they are educated in some sense.
Right. Yeah,
And
definitely. Like,
I'm sorry.
sorry. Yeah, definitely. I think you're totally right. And so here you can see that all of the cities that you can name in China, like Beijing or Shanghai, Chengdu, they got the monitoring first. So there's
Right.
definitely sort of which city got monitoring first in terms of like which hierarchy it is. Like most of the city actually get the first wave if they are a first kind of hierarchy city, like tier 1 or tier 2 cities. But the type of variation what we're going to use though is sort of like at this month when the city starts to broadcast pollution, let's look at sort of shortly before versus after that city starts to publishing data. What do we see in terms of behavior and health change as a function of the time when the city starts to sort of have pollution information? And we do have like staggered rollout. So at some period when Beijing is getting, for example, pollution data, the nearby city like Shijiazhuang, it doesn't have it, right? So this is also a second layer the variation we use, which is geographic variation. But I'm going to show you in later when I present the results that the primary source of variation, I think of it as the exact month when, for example, the January 2013, when Beijing starts to publish air pollution data, what happens to the Beijing citizen in terms of their behavior before versus after they start publishing it.
Okay, so maybe I want to elaborate a little bit on my question. So my concern is you think about so the governments when they roll out the program,
right?
And so the government like strategically decide where they're going to roll out. So basically, so they are going to roll out in a city. So they understood or they anticipate the awareness of pollution is much higher or much. So they have much more pollution aware citizen. So right. So in other words, if they do not roll out in that city, so they are going to get backfire or get unhappiness, whatever. So in that sense, maybe your results is kind of, you see what I'm saying, right? So they just like forward-looking like a rational expectation. So I wrote out in that particular city because they're new. So the citizen there, if they don't, if I don't roll out the information or don't roll out the monitoring, so they are going to get angry or whatever. So you see my point, right?
Yeah, I see what you're saying. I mean, I think there's definitely like the government do want to. I mean, there is a reason they don't kind of roll out the program first, sort of in the least kind of wealthy or informational disadvantaged like cities, right? So they want to kind of do the pilot in a city where people do have the knowledge background to understand what pollution is once you give them the data. In terms of whether like people are gonna change, I think your question boils down to this, like, are people going to change their behavior anyways? Like even if you don't give them the information, right? Otherwise, like so if all I'm looking at is the variation coming from when you have no data access before to when you have data access. And I'm going to show you the entire causal chain for the same kind of representative citizen in Beijing. What happens when pollution was high, when he does not know pollution levels? How does that translate into behavioral changes? I'm going to show the elasticity, basically responsiveness is very low, right? But after the kind of, you have the information, the same amount of pollution variation is going to cause us a larger response for the same citizens in Beijing. Right. So the variation is coming from the before versus after the people have data access. I think I don't get your like rational expectation question exactly like what you're worried about, but let me show you the results and see if your concern is still there.
Okay, thank you.
Yeah, no problem. Okay, so the key research question we're going to ask in this paper is, does information provision alter stuff like awareness, behavior, and health? And ultimately what we want to get at is the value of providing people with this type of pollution information. Okay, so a roadmap of this paper, how we're going to do this. Again, we're going to show you when information changes, how does things change on this causal chain. So what we're going to first do is we're going to first characterize the sea change in information access and awareness, basically tell you what the treatment is, right? I'm going to show you two pieces of evidence. First is that there is actually increase in information access in terms of like mass media pollution information coverage, right? So the media talk about pollution more. Two is I'm going to show you increased awareness, right? So actually when people have higher access to pollution information, the demand for pollution information also increase. I'm going to use web searches on pollution related topics to show you that. So that's the first part. The second part of the paper analyzes the role of information in basically shaping this F function, which is the mapping between pollution and outcome. All right, so there's a huge literature out there that estimates the causal effect of pollution on outcome. Stuff like increased avoidance. People have shown that when pollution is higher, outdoor activities decreases. But what we are interested in this paper is not this elasticity itself, but how does that elasticity, the way that people respond to pollution changes before versus after they start to have information, right? So we look at increase in avoidance. We're going to look at capitalization, which is a relationship between pollution and housing value, right? So where do people choose to live, in a cleaner or dirty neighborhood? And then we're going to look at ultimately health damages, right? So for the same amount of increase in pollution, how does mortality rate, your health outcome changes as a function of availability of information? So the key challenge of this project, of course, is that you don't get to observe pollution until the government start to monitor it, right? So what we're going to do is that we're going to use a consistent measure of pollution, both before and after data availability. So we're going to draw data from the satellite. This is modest aerosol optical depth, which is the picture I showed you earlier on the northern part of China. The nice thing about this measure is available since 2004, I guess. It's like way before the Chinese government started to monitor, right? So the measurement has been always been there. Okay, I hope it's clear like what I'm trying to do in this paper. And let me jump in to show you what the first part. So the first part of the paper is basically telling you what the treatment is. So we're going to document a sharp change in information after city began broadcasting pollution. So I basically going to show two examples. Think about that as one is the old fashioned of getting information. The other is like new fashion of getting information. Like the old fashioned way is newspaper mentions of air pollution. So we scrape data of all the articles ever published in People's Daily, all the way back to 1990. So People's Daily is the official newspaper of the government. You're supposed to read that. And so on the y-axis, I show you the number of daily issues. There are 30 issues in a month. I show the number of days with any smog mentions, either in the news titles or in the news articles, right? So what you see here is that the word smog, so we've also tried other words like air pollution or atmospheric pollution, but the frequency of these terms are basically zero in the 1990s or 2000s. A little bit of a pickup in the early 2010, and then just starting the month of 2013, you see a huge jump in terms of the frequency, right? So after 2013, basically the topic of smog became from a weekly topic basically to nearly a daily topic. Now this is only showing you a pure time series. A lot of things can happen before versus after 2013. So what we can also do is that we text mine the every articles we scrape, and we look at the list of cities that it mentions, right? And then what we do is that we use that kind of list of city mentions to build a panel data at the city and daily level, right? And then what we can do is I can show an event study, which is on the y-axis is a standardized, mean zero standard deviation 1, smog news mentions as a function of time, which is quarters, relative to when a city began monitoring. All right, so 0 is the time when the city began to have monitoring data. So for Beijing, it's January 2013. And for places near Beijing, like Shijiazhuang, it's like October 2013, right? So basically you have a staggered event study. So what you can see here is, again, the standardized smog news mentions is close to 0 before, and an increase to something like by about 0.5 standard deviation after the intervention.
So
right?
excuse me.
After the city have information, there are a lot more news articles that mention smog and also that particular city. Your question?
Yes. So here, so I just wondering, so do you have any measure regarding to how the citizens, so they receive the news, or they really read the news?
Yeah, I'm gonna show you later. So I
Okay.
can't know exactly like whether people read the people's daily like readership, but like that article. But I can show you, for example, web searches. People do like inquire sort of information about air pollution much more when the city starts monitoring,
Good.
something
Thanks.
like that. Yeah. But for the first part, we're only looking at access, which is like, are there more sort of information availability, of pollution if people want to get it, right? Okay. So that was the old-fashioned way reading newspaper. The new-fashioned way is mobile app, right? So this is data from Apple's API, the China version of Apple API. So what I'm showing you here is the distribution of the time when pollution-related apps are related, right? Which is a blue line, versus the distribution of release time of other apps, right? So you can see that by the time that I scraped the data, which is December 2015, you can see there's a huge jump around 2013 January when a lot of apps starts to incorporate air pollution data, right? So that's an increase relative to the rest of other like apps, things like gaming, and music, and video, or reading, or finance. And you might have some question like, why do you have sort of apps about air pollution right before 2013 when no pollution data has been available? We actually dig into what these apps are. Now it turns out these are weather apps. So they used to only report like temperature and precipitation that later incorporated pollution information as of December 2015. Right. So anyway, this is like technical detail, but what I'm showing you here primarily is the fact that you have a very large increase in the availability of pollution-related mobile apps after 2013. Right, so that is access. And now I'm going to speak to Zhigang's question on, do people actually, now you have increased access, do people actually take that into account when sort of pick that up after 2013. So what I do here is looking at awareness. And the way we're going to capture that is we're going to examine changes in web searches on smog-related topics after a city began monitoring, right? So smog is, why do we use smog? Again, smog is a buzzword for pollution. If you have Chinese audience like Zhigang, the exact Chinese term we use is wumai, which is a Chinese version for smog. And so the data we have is city by weekly web searches from Baidu.com. Baidu is like it's the Google of China. It's like it's the go-to search engine in China, and so the Baidu search index is just like Google Trends. It measures the intensity of searches for a particular term, smog in this case, relative to the search intensity for all other topics at the same week for the same city, right? So it's measuring intensity. So here I'm showing you two panels. This is just the kind of analog of the two figures I showed you earlier. The left-hand side is a pure time series, a search index, the raw unadjusted search index as a function of absolute time, right? So starting in 2011 to end of 2015. And again, you can see this like orders of magnitude increase in search index for smog starting January 2013. And on the right-hand side, we sort of disaggregated data to the city by quarter level. So this is, we know for each city in each quarter, when do they, what's the intensity of search for smog. So this is showing a standardized smog search as a function of time, again, relative to the city begin data broadcasting, right? So what you can see again is that it hovers around 0 before, and it jumps by, again, about 0.5 standard deviation after the city began broadcasting pollution, right? So not only pollution access increase, but people are searching about pollution stuff more. Right? So you might think that searches for pollution is just one proxy. They don't necessarily have to do anything, even if they search. So what we do is that we also collect data. I think this is for 50 cities, the best we can do. This is actual sales of air purifiers. All right, so these are like kind of $50 or $60 kind of HEPA monitors. Sorry, HEPA air purifiers that you can put in home that filters the air. And we have data since 2012. Again, you can see kind of a mirror image for from the previous slide. You see that the sales of air purifiers jump almost double since January 2013 when the program began. On the left-hand side, and the right-hand side again, I'm showing you the event study plot, right? So the log per capita air purifier sales jumps up exactly when the city began publishing air quality data. Okay, so I've shown you access, I've shown you awareness. Now I'm gonna do is I'm gonna go to how does the information availability changes behavior. Now, before I do that, because a lot of pieces, I'm gonna talk about avoidance, I'm gonna talk about things like residential choice and health. So I'm going to show you a simple 4-line models that stitch everything together, right? So think of about that as a conceptual framework. So we're going to have a very simple model that starts with a classic Becker-Grossman health production function. And then we're going to add 2 layers to it, right? The first layer is that we're going to allow agent to act to avert pollution's health damage. This is following the previous literature on avoidance behavior. And also, we're going to allow agents' perceived pollution level to actually differ from the actual pollution they experience, right? Okay, so again, a 4-line model. First, we're going to have a health production function. So the health H is going to depend upon pollution C, which is the outdoor air pollution concentration, and A, which is avoidance behavior, things like staying indoors or defensive investments or residential choices. So the key component of our model is that we are going to allow agents to have their perceived pollution to differ, potentially differ, from the actual pollution, right? So people make decision based on the ex ante perceived level of pollution C, but their actual health is going to depend upon the ex post sort of actual pollution exposure. Right? Now, what you can show under common regularity conditions of the utility and health production function is that a utility maximizing individuals is going to exhibit avoidance behavior, right? So when pollution increases, I'm going to show that A, or things like air purifier or air mask purchases, are going to increase. And finally, we're going to assume that the monitoring program eliminates the information wedge. So we're going to assume that before monitoring, the agents underestimates either the level of pollution or the damage of that level of pollution. And after monitoring, the information wedge is eliminated. All right, so from this kind of 4-line models, we can derive 2 main sort of predictions that we carry to the data. The first is that after the information program, we predict that the avoidance behavior, the amount of avoidance behavior we see is going to increase. The second empirical prediction is that the same amount of pollution exposure does less harm to health after people get pollution information, right? So what we're going to do next is that we're going to quantify that something we call the value of pollution information. You can derive that from the first order condition, which is the direct utility gain from being able to know the data, the wage increases minus the avoidance cost, things like the money you have to spend to buy air purifiers and stuff. They're going to be measured, the utility parts and avoidance parts. We'd also talk a little bit about implementation. And then at the end of the day, I'm going to tell you whether the information program appears to be worth it to implement given the utility sort of health improvement and avoidance cost.
So Eric.
Yeah.
So one more question. So I understand this is a short talk, so you cannot go to the detail of the model.
Yep.
So quickly, so here, so you do not consider I mean, in my language, like a general equilibrium effect. So for example, you do not consider so how my behavior is going to change in terms of creating pollution.
Right.
So, but
right. Exactly.
I just wondering, so how important is that?
Right. So I think you're totally right. So after people start to have kind of pollution information, that might actually not only, for example, they might go outdoor less, And what carries with that is that you use private vehicle less or things like that, right? And then that can sort of in turn changes the level of pollution, and you have this loop, right? So like after monitoring, you can change the pollution levels. So so the model is sort of a conceptual framework. We don't intend to capture everything. It's sort of like a minimum amount of sort of mathematical structure that you need to generate the empirical prediction. But we actually look at the data to see if the monitoring program itself has improved air quality. This is something we can actually see in the data. So what we found is that if you look at air quality, the general level of air quality, since in China since 2013, many of you might not know, but since 2013, the air quality in China has improved by something like 40%, right? So like dramatic increase. Part of because of a lot of other regulations that the government is implementing. You know, I mentioned that part of the reason that I started sort of monitoring air pollution is that they have like 5-year kind of plans they want to install to kind of improve air quality. And the first thing, of course, you have to monitor them. So except for like if you parse out the general declining, like the overall trend of air pollution, the monitoring program itself, right, so conditional on the time trends of the general decline of air pollution, the monitoring program itself doesn't change air quality, right? So it's not true that once the city starts to implement implement the data sort of disclosure program, the air quality changes as a consequence of that. At least we cannot detect that from the data. So that's partly the rationale that we shut down that kind of feedback in the model. Does that partially answer your question?
I guess so. Again, so maybe my question is just too lousy because this is just too complicated. So the
Yeah.
other thing I want to mention is in the morning I was reading these issues of economies. So basically, you can see there's like a divergence in terms of government's reaction or opinion regarding to climate change.
Yeah.
Like Japan and China, they decide to go to like carbon free or emission free in like a mid of 2050. But
Yeah.
US seems like go to the different direction, right?
Yeah.
So you see my point, right? So certainly, so this awareness is going to change. I don't know. So it's probably just too complicated because
Yeah. I
right.
think a lot of that awareness is one thing. The other is people's attitude, right? So like you can be perfectly aware of the issue, but you don't think it matters or you don't think it is important. And that could be influenced also by like general political or like public opinion sort of environment. Yeah, that is totally true.
Yeah. Thanks. Yes. Please go.
Okay.
Okay.
Yeah,
Thank you.
thanks. Right. So much for the conceptual framework. So now I'm going to tell you a little bit more about how do we carry those things, how do we sort of implement that empirically. So basically, to put in the simplest term, we're going to basically estimate the change in the slope, right? So what we're going to do down to the ground is that we're going to regress the outcome, let's say avoidance or health at a city C on week T on a measure of pollution on that city in T. And we're going to look at the interaction, which is the pollution and the information dummy, all right? So basically how to interpret beta, the interpretation is basically the change in the correlation between pollution and outcome before and after the program, right? So before the program implementation, you have a correlation between pollution and outcome. After the information program, you have a different pollution and outcome correlation, and the beta is estimated the difference between those two correlations, right? And so why is that different from the existing literature? The existing literature basically is focusing on estimating correctly beta, right? Which is the effect of pollution. So if pollution increasing by unit, how does that change outcome? And there's a big like a causal effect literature on that. And here we focus on beta, which is a change in the slope due to information program. And the question, of course, is how do you get a consistent estimate of beta, right? And so we show in the paper that you have to satisfy two assumptions in order to estimate a beta causally without having to estimate an alpha causally, right? So let me walk you through those two conditions. One is that, again, we require the treatment dummy, which is the information D dummy, or the rollout of the program, has to be exogenous, right? So conditional on my control axis, the epsilon have to be orthogonal to the treatment. So we have two pieces of empirical support to that. The first is that the program rollout is largely determined by cities' administrative hierarchy, right? And these hierarchies are determined like in the 1980s or things like that. So just let me show you this picture again. The cities that get the rollout first are the cities in the highest sort of hierarchy, the tiers. And the way to visualize those is I make this table, and what you can see here is, it's hard to explain, but basically what it says is that if the policy is really implemented as it does, which is the tier 1 city should be wave 1 city should be provincial capitals, the Jinjiang area, the Yangtze River Delta, the Pearl River Delta. The River 2 is the 2007 National Improvement Priority List, the 1997-2012 National Environment Protection Exemplary Cities, and wave 3 is the rest of the city. If the policy is actually implemented by these like predetermined hierarchies, you would have seen dark blue in all of the wave 1 cities, light blue in all of the wave 2 cities, and all white in wave 3. The actual implementation has some kind of a deviation from the plan, sort of the, what they say they are going to do, but the deviation is not very large. And what we do in the paper in the robustness check is that we also kind of restrict to the city where they fall in the correct kind of cubic, right? And basically what the takeaway here is that the determination of the rollout waves are determined by pre-designated things like which cities are provincial capitals or what are Jinjiang, rather than by stuff like the pollution levels or things like that. Okay. And I think, so that's only just one kind of justification. And I think the most powerful thing is basically the parallel trends test, right? So what you want to see is that there's no pre-trend in the beta estimates, right? In the pre-period, followed by a sizable break at the time of the treatment. Okay, so basically, once you condition all your controls, the beta is going to behave very stably until the treatment kicks in when it changes its level. Okay, so that's the first set of assumption it has to satisfy, which is the traditional kind of exogeneity assumption. The two is that in order for the interaction beta term to be causal, we derive in the paper, there's proof in the appendix, that the treatment has to be independent of the pollution level itself, right? So conditional on the controls, it has to be true that the treatment doesn't change the level of pollution itself. This is actually what Jigang pointed to earlier. And we actually, again, tested in the data. So let's look at the blue kind of cells. So we regress pollution or log pollution and indicators for before versus after sort of program, controlling for stuff like overall trends in pollution, like a city, week of year level. So column 1 is our kind of the most lenient specification where we have city, week of year fixed effects and year fixed effects. We gradually phase in more kind of streaming fixed effects. In column 4, we have city fixed effects and region by week of sample fixed effects, right? And across the column, we see a very small coefficient, right? So like after, for example, the information program, you see pollution increases in the by only 0.15%, something like that, right? Okay, let's see what I'm going to talk about. All right, so the proposition in the paper is that the OLS estimate of beta is going to be consistent as long as assumption 1 and 2 are satisfied, even if the level in alpha is not. And we provide a intuition sort of the appendix, which is basically think about as the bias in the slope estimates the pre versus post treatment is going to cancel out once you have these two conditions being satisfied. Okay, I guess from this on you can forget about the technicality because we're gonna do things in graphs and things are gonna be clear. So how are we gonna do this implementation wise? So we're gonna have city by weekly level data from January 2011 to April 2016. For mortality, we actually have data until December 2016, so I can show you longer post period. So I'm going to show you for every outcome event study of beta, the coefficient. I'm going to show you table reports point estimates. Excuse me. I'm going to show you the same set of specification fixed effects changes for robustness and the cluster standard errors at the city level. In one exception, so all the outcome and examine, I'm going to show you the same set of specifications. One exception is for housing transaction data, which we only have for the city of Beijing, but estimation equation is going to closely mirror the one above, right?
So Eric, so gamma, so that's essentially what is gamma is
Right, so X gamma here is just like a control matrix. Think of this as like city fixed effects, right?
like
And then you have
including
like
what?
weak up here, and the gammas are just the coefficients of the fixed
Sorry,
effects.
so X prime, so includes what?
Oh, it includes, so I'm going to show you tables, but basically it includes things like city fixed effects, week of year fixed effects, and year fixed effects, and also other stuff that could be correlated with both pollution and outcome, including things like temperature and precipitation.
No, so actually, so what I was interested in, this is just circle back to my earlier concern.
Right.
So I was thinking, so X, you probably need to include like education, income, and even you probably need to include like industrial policy in that city.
Right. So anything that changes at a city year level, for example, if you think that things like the average level of income and education in the city and year is going to differ, right? That is absorbed by things like city by year fixed effects. We're going to have those. Yeah.
Oh, okay, so you consider that.
Yeah. Yeah.
But so do you consider like different cities, so they have different industrial policy? Let's say, for example, some city really relies on those industry, but that industry is pretty like pollution heavy.
Right. So definitely, like if you, so we're gonna have city fixed effects. So anything that is different across different cities are getting absorbed, right? So our city A has larger fraction of mining relative to city B.
Right.
That's going to be absorbed by city fixed effects. So the only thing that I say would kind of, confound the beta coefficient is going to be things that correlate systematically with the rollout of the program. For example, if there is a program that also kind of change industry policies for the same set of wave one cities, exactly at January 2013, that type of thing is going to sort of confound the beta estimate. If a policy that only changes sort of at the year level, right? So it's just like Beijing in 2013 and 14 is different, but it's not systematically correlated with the way that a policy rollouts across the nation, it's not going to matter because it's absorbed in the fixed effects controls.
Okay, thank you so much.
Right, yeah. And we discussed in the paper, we searched like meticulously for any policy that could potentially correlate with the rollout. And we consider, I think, 4 or 5 of them that can potentially be kind of correlated, and we don't find evidence. And the other thing is, I think like any industry policy that matters for pollution, very likely is going to change the level of pollution, right? So if you control emission for a different city, or if you give like subsidy to a different, for given industries, if it's a pollution heavy, that probably is going to change the pollution level either up or down. And a part of the evidence we found earlier is that we actually don't see that sort of a pollution level changes as a function of the program itself. Okay, so let me see, I have like 15 minutes left. Maybe enough to walk you through briefly the results. So the first part, let me show you again the roadmap. The first, I'm going to look at avoidance, and then we're going to look at capitalization, which is like, think of it. So think about avoidance outdoor activities as kind of a short run or short-term way to avoid pollution. Housing value, think about that as the long run, sort of a long-term way to avoid pollution. And think of a mortality as the ultimate outcome that you care about. Okay, so for short-term avoidance, we're going to analyze the relationship between pollution and outdoor activities. Again, we're not interested in how outdoor activity itself respond to pollution, but we're interested in how changes in the Wallace coefficient between outdoor activity and pollution as a consequence of the intervention program. Now, how do we measure outdoor activities? So we have data from the universe of credit and debit card transactions in China between 2011 and 2016. So we have administrative data from UnionPay. UnionPay is the only card transaction clearinghouse in China. So as long as you swipe a credit or a debit card in China, that's get captured in our database. So the total value we capture in our database is something like $66 trillion, which is about 59% of national consumption, or about 22% of GDP. We're unaware of any other data set available that can do better than what we do here. So at the end of the day, we have like 2.7 billion cards in 2015. Massive data set. What we end up using in this paper is 1% random card sample, although we have run it with 100% sample and the results are just very similar. Okay, so this is basically showing you that we're capturing a big share of total consumption over time. All right, so the left-hand side, we have outdoor activity measured by card transactions. On the right-hand side, we need pollution. How do we get pollution? The pollution data is from the aerosol altimeter depth from NASA's Moderate Resolution Imaging Spectroradiometer, or the MODIS algorithm. It's measuring aerosol concentrations, things like sulfates and black carbons, these like particles, in the air column corresponding to 10 by 10 kilometer ground area, right? So when a satellite passes a location, it looks at the entire column of air. It infers by the reflection and absorption of sunlight how much aerosol is captured in that kind of column of air. And we're going to use that to proxy for particulate matter pollution. Right? So we aggregate that data to the city weekly level. So for each city and week, we observe sort of the proxy for particulate pollution. And why do we use that instead of monitoring data? Again, we don't have monitoring data before governments start to monitor them. So the key advantage of the satellite data is it's available both before and after monitoring data. And we're going to use that throughout our analysis. All right, so this is just showing you the data that actually have signal. The left one is just taken directly from a job market paper. So the y-axis are PM2.5, the particulate pollution at the ground level. On the x-axis are MODIS, like satellite data sets, measures of particulates when the satellite overpasses the monitor, all right? And this is basically showing you the bin scatter. You cut all the satellite data into 100 bins, and for each bin, you plot the average of the PM2.5 on the ground. It's a strong correlation. On the right-hand side, we replicate that for China. For the post-monitoring period, we found also a very strong kind of relationship between the two. Okay, so here is the first main graph I'm going to show you. So I typed the equation on top of the slide, but basically what that is this is showing you the change in the correlation between air pollution in the city and purchase rates, as what fraction of people go outdoors and make purchases. The correlation between those two variables, of course, controlling for all the fixed effects and stuff, as function of time relative to the city begins monitoring, right? So the minus sort of period are periods when the cities don't have monitoring data. And the positive kind of quarter since monitoring, like the positive period, event time periods, are the correlation when a city starts to have data. Okay, so what you can see here is that the correlation between pollution and outdoor purchases are nearly zero. So like pollution variation does not appear to predict outdoor activities until the city starts to broadcasting data. That's where you start to see that a negative relationship between pollution and outdoor activities. Right? So when the pollution increases, people reduce outdoor activities, but only do so after they start to have information. Right? So what is the beta estimate I kind of talked about earlier? The beta estimate is just the difference between this before line versus the before average minus the after average. Right? So that's the effect of the information policy.
So Eric,
yeah.
One more question. So like for after since monitoring, do you have more data?
No. So unfortunately, what we have is until December 2014, or it's April 2014. So we don't have longer data to have like a longer period. So I'm showing you the balance panel of 8 quarters before and 4 quarters after, and that's the longest we can show you.
No, I'm just curious. So is there any like fatigue?
Yeah, so it could be possible. Like after a while, you're like, it doesn't worth it or something like that. But I am going to show you that for the mortality data, we actually have until December 2016, which allows me to show you 8 quarters after the policy. And it actually turns out that the mortality effects takes time to show up, and the largest decline is actually after a year. So it does appears to be like people are still kind of avoiding after a whole year, something like that. Yeah. Okay. So you know, I'm going to show you a lot of this type of pictures, but just changing Y outcome. But here's the table estimates of what I showed you earlier. So what I wanted to focus on, so this is basically regressing the outcome variable, which is outdoor activities on pollution and pollution interacted with after monitoring, controlling for city fixed effects, week of year and year fixed effects. And then I changed I increasingly add sort of stringency to the fixed effects controls through like column 1 through 4, right? So the key parameter, the beta parameter, is this log pollution interact with, you know, indicator after monitoring coefficient. And the way to interpret that coefficient is approximately after the monitoring, the elasticity of the pollution at purchase increased something by 2% or something like that, relative to the average level of purchase, which is 860 transactions per week per 10,000 cards. Okay. All right, so that's just a numerical way to summarize the figures. And we have other like supportive evidence that we think it really, this is about avoidance. So we found that an increase in avoidance concentrated in deferrable transactions. So for each transaction, we can see what type of merchants they go to. Do they go to supermarket, dining outs, and parks and movie centers? We think of these things as things that you can kind of defer, right? So we can wait a week or two to do. And we think these type of consumptions are more likely to subject to avoidance. And actually in the data, we found that the entire effects are driven, almost entirely driven by these categories, deferrable categories, whereas all others categories, we don't see a significant changes after monitoring, right? So if you want to go out and pay the bill, you have to go anyway. Okay. So given a time frame, I'm going to skip this effect size discussion. Just telling you the effect size we found is not crazy, and there are robustness checks that you can look at in the paper. So I'm going to talk about the second part of the analysis, which is if you think about outdoor activity as like a day-to-day short run kind of avoidance, there's a literature in the economics that also talks about the long run avoidance, which is think about how do people choose between like dirty versus clean locations for residents, right? So we're going to take that literature, but again, rather than estimating the degree of capitalization, you know, how pollution gets capitalized into housing prices, we're going to look at how does that relationship change before versus after people start to have information, right? So the data we have now, we only have data for one city, which is Beijing, and Beijing starts to monitor in January 2013. But luckily, we have like transaction level data. We have all new home transactions in Beijing from 2006 to 2014. About 0.6 million transactions. We see price, apartment characteristics. And one limitation is we only see new homes, which is about 40% of all housing transactions. And we are happy with that. So again, I won't walk you through the equations again, but this is basically what I showed you earlier. We're going to regress an index for housing prices adjusted for apartment characteristics, how large it is, which floor it is on. And we're going to regress that kind of hedonic adjusted pricing index on pollution and pollution interactive with post policy. And in the case of Beijing, it's just like post 2013, right? So I'm going to say that in the paper, we show, what we do is that we use two different types of measures for pollution for supplementary analysis. One is that we look at satellite at the apartment level, and two is that we use distance from the apartment to the nearest major polluters. For the sake of time, I'm going to only talk about exercise 2, which is we are going to look at all the big polluters in Beijing. Right. So we have industry like facility data, and we focus on top 10% of the polluters, which is about 41 of them. that in total account for almost 90% of total emissions in Beijing. So these are really big facilities. And these are the locations. This is a map of Beijing, and the triangles here are the facilities. And we have the location of the housing transactions. And the question we're asking here is, if you think about the relationship between how close you are to the polluters and the housing price, how does that kind of slope, right, change before versus after people start to have information? Right? So before 2013, you might think it's okay that you live like 2 miles away from a chimney. Now you think it's not okay, this type of thing. Now, again, this is the same picture. Unfortunately, now I only have like data for 2013 and a 4 month of 2014. So I can only show you 1 year post trend. But basically what I'm showing you is that the correlation between distance, proximity to polluters and housing prices also jump towards the negative direction by about 0.10 percentage points, 10 percentage points, right? Okay, so after pollution information campaign or this program, housing prices are more responsive to pollution variations after this information campaign. And again, we discussed effect size, showing you this is not crazy. And I hope like I can jump into the final part of the analysis, which is looking at health damage. Okay, so this is the end point of analysis, which we think is also the most important. We talk about avoidance in both in the short term and the long term, but we don't directly care about avoidance. We care about people's health, right? So the ultimate reason that we control pollution is we hope less people can die or suffer from disease burdens from those shocks. There's a huge literature in environmental economics that estimate the effect of pollution on mortality, which is an extreme but very important outcome for health. So here what we do is, again, we test for the change in the relationship between mortality and pollution before versus after city have broadcast pollution data. And the mortality data is, we have city by weekly level mortality rate for 131 cities in China from January 2011 to December 2016. The data is from the China CDC, the disease surveillance point system. So our data covers about 73 million people, which is about 5% of representative sample of population. So here is the same figure I showed you earlier, but then I'm replacing the outcome to log mortality level. So again, because we have like longer data, I can show you the longer sort of post period. We can see here, again, it's kind of a flattened, stable mortality and pollution sort of gradient, which starts to drop after cities begin to have data, right? So what I'm going to say here is that the interpretation is, for the same amount of pollution increases, the response of mortality becomes weaker before versus after, right? So in this case, we see about 3.2% reduction in the harm, basically, of pollution, of health harm done by pollution exposure. Okay. What we do, we also look at different causes of death. We found that cardio and respiratory death, which is conventionally thought of as linked to health, accounts for over 50% of all the effects we found, which is good. We don't find effects like injuries, which we think of it as a placebo test. That doesn't show up, which is good. We see larger effects in urban areas, places with more hospital access, more electricity usage, higher mobile phone penetration. And also we found exact heterogeneity patterns for outdoor spending, right? So if the city reduced outdoor spending more in response to the information program, we see a larger mortality benefits as well, which we think makes a lot of sense. All right, so the punchline of the paper is that we apply a kind of a back of envelope VSL calculation. We show the mortality benefit of this program is about $73.3 billion per year. That's something about 150,000 deaths for age 60 plus for the entire China. What we do is that we also look at mortality benefit, which is about 48.8 billion per year. And relative to, we look at morbidity benefit, which is about 2/3 of the mortality benefits. We took that number directly from the literature that looks at like things like medical spending. At the end of the day, we're going to point out that the avoidance cost itself, things like mask purchasing and like air purifier purchasings, or things like foregone consumer surplus because you're not spending that much, is we calculate that to be something around $12 billion per year, which we think is much smaller than the mortality benefit and morbidity benefit of the program. Okay, I'm a little over time, but let me conclude the paper. So we think we're the first comprehensive analysis of a national-wide pollution monitoring disclosure program. We show that information is a key determinant of avoidance behavior, leading to a cascade of behavioral changes. Behavioral changes in turn mitigate health damages. And at the end of the day, we conclude that the information program is a kind of low-cost environmental regulation and an important lesson for other emerging and developing countries. Thank you.
All right, thank you so much, Eric, for your great presentation. So do we have any other questions from the audience? So we have some colleagues that left early, so this is like Friday, so they may have other meetings to go. Yeah. Okay. So I mean, just again, just circle back some of my question, but certainly this carefully are executed paper. So you guys did tons of work. It's very convincing and very interesting, very important, I guess. All right. So a couple of minor things. Number one, so it seems like, so now I understand. So you are more focused on the behavior change on consumer side. Right. And then so, but then so you focus on, I mean, there are like two minor things. I don't know. So whether you have do some like a control or not. So you look at Apple, and I mean, when I say Apple, essentially it's like the iPhone App Store, right? So it's number one. Number two, you look at Union Pay, right? And the reason why I bring up these two issues is so you may have kind of biased sample in the sense whoever use Apple and whoever use Union Pay, they probably, relatively speaking, so they are higher income, better educated. So in that sense, the impact on them is going to be stronger. So, but I understand. So yeah, so if we look at them, you find out these results that's already interesting finding, but somehow so you may want to.
Yeah, exactly. I totally get you what you're saying. Like we're getting at, for example, the Union Pay analysis. We're getting at the people who actually have the credit card or debit card. They use it.
Right.
That could be very different from like the rural population where they don't have it.
Right.
We actually found it. We for both like card analysis and the mortality analysis, we look at things like income, like urbanization, and things like mobile phone penetration, right? So if 70% of people have mobile phone versus like 90% people have mobile phone. So we don't have like individual heterogeneity, but we have like city level. We can look at high versus low penetration.
Okay.
It turns out that, so places with higher mobile penetration has a larger benefits, which I think in itself is useful because like it tells you not only you need a program, but also you need mobile phones to reach people.
Right.
And in terms of consumption, right? So we don't capture like 100% of the people in terms of like outdoor activities, but we do capture like 60% of total consumption in a national sense.
Right.
That's the best we can do.
Right. I understand. So far, this is already very formidable task to do because you have tons of empirical challenge you have to face.
Yeah.
The other things is so when you say the mortality, so like the elasticity or whatever, so the derivative of mortality with respect to pollution. here's my guess, may not be true. So, or only this is only my hypothesis. So this information improvement may somehow is going to change the industry policy. What I'm saying is, as a response, those polluters or those companies, they were forced to in some sense to change their pollution emission to make the pollution itself less deadly.
Yeah.
Or in other words, maybe, okay, so maybe put another way. So overall, there's like there's a declining trend in terms of pollution. I mean, how deadly the pollution can be. So maybe what we are capturing is just think about it in the margin, right? So you have maybe, so maybe you say, okay, so just put it another way. So just think about, so you have the mortality cause as a function of a pollution. So this is probably like a convex function. So now, so you are just going to capture the highest portion.
No, I totally get you what you're saying. So it's like,
Okay.
so we're controlling for concentration. So it's like, but your concern would be valid if you have, like before and after, we show actually you have the same concentration, like the level of pollution is.
Wait a second. So I'm not, so this is not necessarily a concern, or this is not necessarily criticism to your paper.
Yeah, I know it is, but I get you, yeah.
Yeah, this just says, so maybe something, so, but again, so you guys very smart, so way smarter than me. So
No, I
thought about that. Yeah, you probably always thought about that.
Yeah, I actually think it's important. Like, even if you don't have like a concentration change, right? So it's still like 60, but then you might have industries that change like the composite of what they're emitting, right? So they transfer, like they move from like coal to gas, but they burn more gas, or like they just change the composition of how toxic the pollution is.
Right.
Then you might, that could be the channel, but like.
No, so yeah, so
Yeah.
let me just let me just tell you a little bit of bigger picture. So what I was thinking. So again, so I'm coming from macro, right? So I may always thinking in the macro perspective.
Yeah.
And particularly, so when you show us the picture, like so the slides regarding to the social cause, the social benefit.
Right.
What I was thinking is, so maybe there's interesting under surface, there may be a very interesting two function. Function number one, the awareness of the households as a function of information is going to be a declining function. And other function is, so the deadliness or the benefit of reducing the pollution as a function of information, let's see, yeah, it's declining.
Mm-hmm.
So you see what I'm saying? So yes, once you put more effort and the awareness of the households, the benefit from the awareness of the households start to decline. On the other hand, so the benefit by reducing the mortality is going to decline as well.
Okay.
One is because people get fatigue, right? Like in the US, people get fatigue. The other is because like technology, right? So essentially, so just think about like, so in the macro, we have this decrease in marginal return, right? So in some sense, okay, so toward the end, so you, in order to put you to the frontier of your production, so you really need to pollute a lot. That's when you close the frontier. But if you are inside the frontier, so in terms of production, so your pollution is going, you see what I'm saying, right?
Yeah. So it's more like a short run thing, right? So like in the short run, you might have like a very strong reaction, but then over time, if I treat you with the same information, you might not be as attentive to how you work.
Yeah, so both from supply side and the demand side is going to squeeze you.
Yeah.
Squeeze you in. But yeah. So again, so this is just for sure. This is not a criticism. Just these are like brainstorm. So
yeah. No, I think these are important. Yeah, I think this program is relatively new to China. Like everybody is using app, but it'll be interesting to know like information fatigue as a general topic, because like we get warnings and things like all the time, right? So we look at COVID numbers. After 3 months, we're like, what the, right? So it's like all of a sudden 1,000 seems like just 1,000.
Okay. So I guess we should stop here. So it seems like everybody are gone.
Okay.
So we just stop the recording.
Thanks.
Okay. Oh yeah, thank you again.
Thanks.